All right. Hello, everyone. My name is Konstantinos Karanasos. I'm a software engineer at Meta's data infra working on batch compute engines. Today, we're going to be talking about PySpark meets Velox, or like our take on how we're redefining efficiency for our ML workloads. This figure up there, I was playing last night with Meta AI. Its take on what it means PySpark meets Velox. I don't know which one is PySpark, which one is Velox. Yeah. Let's start by looking, you saw at Pedro's presentation, the slides as well. This is the general figure of how the AI lifecycle looks at Meta. You see at the bottom right there the lakehouse. So this is where all our data lands from logs, from various different types of data. We have the lakehouse. We do a lot of data preparation to prepare data so that then we can use them for training machine learning models. You see at the bottom this training line there. We have DPP that Masa talked about that loads the training data, and its purpose is to keep the GPUs busy. So then we use the GPUs to train the models. We get the models, we deploy them in production. Then they are used to do predictions by users. And then there is this whole loop there that as predictions happen, we log data, and then we keep on doing this process. What is very interesting is that we see an important shift in our workload. So the majority of our workload at Meta now is fueling machine learning and AI use cases. This means that we no longer have only the traditional analytics we are used to all these years. There are different query engines that are used in the lakehouse for data processing. Spark, Presto, and DPP are the most widely used ones. Presto is used more for like the interactive type of scenarios, like lower latency, dashboards, etc. DPP, Masa talked about. Spark is what we're going to be focusing in this talk. And let's look a bit at, in general, batch compute for AI. Spark is the main engine used today for all the data preparation of our various AI, ML, GenAI use cases. Meta maintains one of the largest Spark deployments worldwide, if not the largest. Following the shift I talked before about going from traditional analytics to more fueling AI and ML use cases, we see that SQL used to be for many years the only language that our users could use in the warehouse. Right now, we started offering PySpark relatively recently, a little bit more than a year ago. We see massive adoption, and the reason is AI. People are much more eager to use Python for all their use cases, for all their third-party libraries, and so on. Let's look a bit at how our use cases look like. So we have two main categories of users. The one is our recommendation systems. Basically, the idea there is batch compute engines want to enable efficient data preparation for our recommendation systems, and that's across our products, from ads, Instagram, all the feeds, everything your billions of users worldwide are interacting with. And the second big pillar is GenAI. You are all familiar with the Llama models. They use massive data to be trained. All those have to be somehow pre-processed. So one of the main focuses is how do we provide all the data to build state-of-the-art Llama models. Let's focus a bit. Let's double-click on the recommendation systems, and let's look at what we're calling feature injection. So the idea here is that we want to add some new features to our training tables, and we want to do that within hours so that we can enable fast experimentation. Until now, that could have taken even up to days, and we want to bring it way lower so that our ML engineers can fast iterate to produce the best models. On the left, you see we have this training table. It's a toy example. We have the user ID on the first column, user 1, 2, 3. And then we have a feature map. So this is the way we typically store our features. We have multiple such maps. But the idea is that we're using maps instead of columns because we have deeply nested structures, and we also want to keep the flexibility for schema evolution, adding new features, etc. So you see there some F1, F2, some features. What the ML engineer wants to do is wants to play with some new data. So in order to do that, they want to inject some new features in this map. So they use this other table. Again, we have the user 1 and user 3. The target map is this feature map 1, and then we have these F5 features and their values that we want to add. And the result, of course, this looks like, as you all know, it's clearly a join. We want to join the left and the right tables, and the result will be this new map that has been updated with the new features. Now, where this gets complicated is that first, users are in the order of billions. The second complication is that features can be tens of thousands, right? So we have, or even more features. This is not your traditional data analytics. And then we have several questions that are coming up. First of all, how can we perform this massive join fast without taking several hours or days to complete? The second one is, let's say we use Velox. How can we control what exactly happens in the engine? How can we really have tight control of the execution of the plan that gets executed so that we can squeeze the best performance out of this massive join? Another question is, how do we control storage optimizations when we have these maps? Pedro mentioned we have this optimization, the flat maps, but how exactly do we allow the writers to optimize this further is an open question that cannot be easily done. And then a last question is, how can we avoid rematerializing this whole table with all the users and all the tens of thousands of features just to add one new feature? And through this example, this brings us to our main challenges here. First one is data scalability. So all the AI and GenAI workloads are increasing our demand for data scalability by orders of magnitude. The second big challenge is wide tables. Unlike traditional analytics, tables for ML can be really wide. And by wide, this means both number of features, like we see, for example, in all these recommender systems, but it can also mean much bigger, like each row can be much bigger, each column, basically. So think of it like in GenAI, you can have multimodality, you can have whole documents and websites being stored, so we also have much bigger tuples. Another observation is that we have custom user logic much more than we used to. So in AI and ML, people use third-party libraries. They include their logic that cannot be expressed as traditional relational operators. And all this brings pressure to our engines for how can we do that more efficiently. Another challenge is data mutability. So applications often need to just update a very small fraction of the data, and we need to do that efficiently. And then we also have what I consider as dev productivity and fast experimentation. We want to allow our ML engineers to very quickly go through this new data to be able to experiment and build new models. What you see as a non-challenge here is that we don't have also the typical analytics here that require heavy query optimization in the sense of 5 and 10-way joins like we used to have. So we see similar computation in that sense, but very different challenges. What are the existing solutions we have in hand so far and that people are using in our lakehouse? The first one is Spark, so what I call vanilla Spark. So it has proven its scalability and it has been battle tested throughout the years, but the very execution of the engine doesn't include vectorization, doesn't have native execution, so this leads to scalability limitations. And of course, what this means is that our users become very crafty about what they can do to circumvent all these problems. Most of it happens through UDFs or Spark C++ transforms. If you're not familiar with transforms, basically it's a C++ process that is running next to the main Spark executor, and then Spark reads the data, pushes them to transforms, and then gets them back. The problem with that is that there is no reusability of components. Like the moment the customer creates this solution, no one else can use it. The second one is, as I described, by Spark reading the data, we have heavy serialization costs. Now, people have tried to bypass that by reading data directly from transforms, but then if you want to do vectorization, if you want to do all this more low-level operations, you have to rely on the application user to do it, which leads to a lot of reliability issues. Whenever something changes up the stack, we have SEVs, etc. And also, there is no out-of-the-box support for Metal Lake. Metal Lake is our version of, let's say, all these mutations, iceberg, kind of thing that Darren is going to talk to you about later today. Also, no support for different file formats. And then the other thing that we're observing is that we have use case specific services that are created by our customers, are tackling a very, very niche problem, and they cannot be reused. So these are bespoke solutions that often eventually become unreliable and cause problems. So our solution to all this is what we call PySpark Velox, which brings abstractions for native execution on top of Spark. Our goal is to combine Spark scalability with Velox's efficiency and performance and Python's ease of use. This is the high-level architecture. You see the user on the left. What they do is they're specifying their pipeline with a Velox execution spec, so it's the specification of what they want to execute. Then you will see that we have, this is basically a PySpark framework, a framework built on PySpark. We have the PySpark Velox runner. So the first step there is to create the committer so that we can, whatever results we get, we can commit them to the metastore and write the data, and we generate Velox tasks. The way we do that is we take this specification from the client, we build the Velox plan in C++, we generate ourselves the split, so we look at the metastore, we look at all the input tables, we generate the splits, then we generate and serialize the Velox tasks from these splits, and then comes the time to run these Velox tasks. In order to do that, we have, at this moment, we initialize the Spark driver. The Spark driver takes these tasks. It starts the cluster with thousands of executors. And then through a Python UDF, we use PyBind, we then initialize Velox. We get the serialized Velox tasks. We execute them. And then as a last step, we commit the result to metastore. So this is the high-level architecture. Let's get into some details of that. So first of all, Velox plan definition. Users specify their execution plan in Python using this Velox plan builder. You see on the right here the type of, no surprise here, we have scans, writes, projects, limit, filter, various types of joins, aggregation. So under the hood, this builds a Velox plan with metadata in C++ through PyBind 11. And we will soon integrate with PyVelox so that we use the more standard way of doing things. You will hear from Krishna about this at 3 p.m. today. We currently support a meaningful subset of the Velox operators, and the way we are doing things is very easy to extend to new operators. We have already support for different types of file formats. We have ORC, which is the default, but now Nimble is the new open source file format that is much better for AI. So we have support for it. And then the big advantage is that we can specify low-level Velox parameters, which has been key for performance. Just a sample of them is, for example, we can have better control of how we use memory. We have various plan optimizations, for example, how we read flat maps to struct columns internally. We have various configurations for different types of encodings. We do split preloading to mask various I/O costs, and so on. So all these have to be, highly specified so that we can squeeze performance. The pipeline execution looks as follows. We have the pipeline class. Basically, this is specified by the customers. They create the execution plan, they create the committer, and then they commit. It's a very simple API. Note here that Velox has a very low-level API of specifying the execution, and so we have to adorn that with some metadata so that we can commit the results, etc. Then you have your PySpark Velox session. We have modeled this after the Spark session. You do get or create. Then you have the creation of the execution plan. You generate the Velox tasks that we talked about before. Then you create a data frame with the serialized tasks, and then you use a Python UDF in order to drive the execution in Spark. Let's talk a bit more about how the execution happens. One concern is how do we distribute the execution? We create one Spark task for every Velox task. And then within every Spark executor, we can run one or more tasks. By default, we run 4, but we heavily customize that based on the use case. It's an open problem how we can do that automatically so that we don't have to, for every use case to fine-tune that. The good news is that we are inheriting reliability and failure recovery from Spark, so we don't have to worry about all the task retries, stage retries, and so on. We have implemented our own commit protocol. We support single partition queries at the moment, and we support different types of commits. So a user can add a new partition in a table. They can override a partition, or they can do some meta lake commits for mutations. And we have various tools for monitoring, debugging. We have a local Velox run so that you can debug just on a single task. What happens, you can run that locally. And we have several internal tools for observing execution. But one caveat here is that it is still challenging given the different systems involved. Some of the benefits were seeing already. First of all, reliability and developer productivity is much better because we have this shared abstraction. So instead of having users specify, create their own custom-built solutions, now we provide these abstractions within PySpark. Cost and performance benefits for high production use cases is the main reason we did all this. It allows us to iterate fast through this, being able to specify lower-level plans. We have clear semantics because we don't have to go through the business of, okay, is this SQL, is this ANSI SQL, what exactly you're doing? It's Velox semantics, so it's very clear to know what happens. We have compatibility with different versions of Spark, so we have an older version of Spark running. We are currently upgrading to the latest version. PySpark Velox will work out of the box in both. And another important part is that we are learning at a smaller footprint. By smaller footprint, I mean for some specified use cases, and then we can learn and bring the benefits back to the main engine. Let's talk a bit about now the level of abstraction, because that is important. For our AI ML use cases, what we are observing is that SQL or PySpark, the data frame APIs, is too high level for us to be able to squeeze the performance out of our plans, but it is at the same time too low level for end users, right? At least at this stage of maturity of our system. As an example, a high-level operation someone wants to do is what we called before about feature injection. We want to inject a new feature in a hash map field of a table and store it as a meta lake commit, right? How are we bridging this gap between this high-level API that our users want and the lower-level API that we are doing? We let customers specify higher-level specialized operators. So we have introduced a feature injection operator. We have introduced a data merging, clustering operator. And then we allow only power users to build actually Velox plans from scratch. Some features that are currently under development. What we have so far in production is single-stage queries. So these are like map-only queries, which means that your tables have to be bucketed and so on if you want to do joins. We are currently integrating with our internal shuffle service. This is going like later in the month. This will be ready. We are doing the data plane through PySpark Velox, and then we have the control plane still being done by PySpark for reusability. Our current focus is on simple DAGs, like simple two-stage jobs with a single reduce, but we are investigating whether we should open this up further. And another big feature we are adding is Velox UDFs. These are already supported internally for some users, but we want to make this more officially supported by PySpark Velox. Adoption so far. We have a bunch of high-caliber use cases across all our AI ML initiatives that are using it. Feature injection across different products are using it. Meta lake compaction. So how do you compact commit so that you're not slowed down by by merging the commits on the fly. This has been already done in PySpark Velox. We have data clustering so that then you can apply better compression so that you save disk space and also read time. Deleting features from tables. This is also something that we are implementing on PySpark Velox and using in production. And then we have some custom file creation for some internal services, which is also done through some file write operations. And we have several more use cases lined up. And now you might be wondering all this time, OK, there is also the open source project Gluten, which is adding support for Velox in Spark. So where are we starting with respect to that? The reality is that we started prototyping Gluten at Meta for the last few months. We see some very key advantages here. The first one is that we have better integration with Spark's ecosystem for like specifying the plans, using Spark's API, SQL, PySpark, all this work out of the box. We also saw, based on our investigations, we also saw a bunch of challenges that came up and that we have to overcome. The first is ANSI SQL compliance. We're trying to move to ANSI SQL for our internal offering of Spark. Gluten is still using the Spark SQL semantics. A second one is that we have to rely on Spark 3.4 for Gluten while we're using an older version of Spark still. We're upgrading it now. Integrating with our ecosystem, we have all these custom file formats, custom shuffle support, custom Metal Lake, and a bunch of different services. This requires work, which is non-trivial. And also there is the part of the SQL part of our workload, which is also still a big part of our workload. It is unknown how much gain we will get once we integrate with a shuffle service. A lot of our customers are using Java UDFs. These have to be rewritten to C++. Otherwise, probably the gains are not going to be as pronounced. But bottom line, realistically, it will take more than a year to move significant part of our workload to Gluten. Where we are right now is our current focus is on the efficient end-to-end execution. We are like trying to push the envelope on that front. And the longer-term goal is indeed to bring this learning back to the main engine, possibly through Gluten, but this will take longer, and a lot of our use cases are much more urgent. So we're focusing on this end-to-end execution for now. Some performance numbers. So we took this feature injection operation that I mentioned before. We ran it in Spark. We couldn't finish, so what we did is we took 1% sample of our data. That took a little less than 10 hours, or a little more than, I think it was 11.9 hours, actually. So you can see that that is clearly for like our whole data that's impossible to ever finish. Then we took PySpark Velox, what we have today. That took about 11 hours. And that was a 75x performance improvement. And then we applied Metal Lake on top of that, and that was another 20x improvement. So the end-to-end system that we have today that can do feature injection actually takes about 35 minutes to complete, up from probably more than 100 hours if Spark finished. And to wrap up, this is the second image of PySpark meets Velox that Meta AI generated. So the success of Meta in the AI ML space relies a lot on the success of our batch compute engines. Rexis and GenAI are pushing the limits of our engines in terms of what is possible. With PySpark Velox that I introduced today, we're combining Velox's efficiency with Python's ease of use and Spark scalability. We introduced a Python API to specify highly customizable execution plans that get distributed by Spark. We have a lower level API through Velox for efficiency and higher level operators for ease of use. We've seen orders of magnitude of performance improvements over production use cases. And all this happened, like we started this, I forgot to mention, at the end of 2024. So we managed to do all this in a matter of a few months. And we have a bunch of exciting future extensions that we're planning to do. We want to bring better multimodal support, vector search, offline inference, and so on. Thank you.